Welcome to 3 crypto challenges from Internetwache CTF 2016. We will have a look at crypto60, 70 and 90. So let's start with crypto60. Alice wants to send something to Bob and it seems to have to do something with RSA. And when we download the files, we see that we get a couple of public keys, 3 public keys, and an encrypted message. And also when you print the files, they do look indeed like normal public keys, how you would expect them. And then the encrypted file has 3 base64 strings, so that is probably encrypted data in a binary format, just encoded as base64. So let's have a look at the public key with OpenSSL. I didn't remember the command, so I had to quickly Google the command again. But with this one, we get all the necessary information from the public key. And we can do this for all 3 files. And what OpenSSL shows us is the modulus and the exponent of this public key. RSA and other crypto algorithms are basically just math. So the public key and private keys are actually just special variables for this mathematical algorithm. In this case, it's a special exponent and modulus. This goes into how RSA works. But what you should know mostly is that the modulus is the multiplication of the 2 private primes. And with those primes, they have to be kept private. If you figure out those primes, then you could recreate the private key and decrypt any file. And the modulus is the multiplication of those 2. And RSA is so hard to break because getting the factorization of this modulus is extremely hard. This prime factorization is extremely hard, especially for long strings. It's basically impossible except for brute forcing. But for especially small moduli and special other weak keys, we may be able to easily factorize those modulus. So what I'm doing now is I'm extracting the modulus in a proper number, as a proper number. So I'm removing the colons and I just use Python to then convert the hex value to an actual integer. And once we have that, we can use services online that help you to figure out if there is a public factorization known for this number. Let's have a look at the Wikipedia page of RSA again to see exactly where this weakness comes from. Well, it's not necessarily weakness. Mathematically speaking, it's very hard. But again, if the modulus is especially small or for whatever reason one of the prime leaked, you can, or a weak prime was used, you can easily calculate the missing prime, and from that on you can find out the decryption. So you can see here that the public key is defined as n and e, and n is the number that is used for the modulus operation and e is the public exponent. And this modulus n that is included in the public key is the multiplication of p and q, and p and q are those randomly 2 distinct chosen primes that you need to keep private. Again, if one of them leaks, you can just, divide n by p, for example, to get q. So it's integral and very important to keep it secret. Also, Wikipedia says here that p and q have to be kept secret because if you can factor this modulus, then you are able to create the private key. And there's this great website called FactorDB, and FactorDB is a database of factorizations of numbers. So when you have a very weak key, you can maybe just give it this big modulus number, and maybe FactorDB knows how to factorize it. In this case, we actually get a p and a q value. We get 2 primes that multiplied together create this big modulus number. So now with this p and q, in theory, we should be able to generate the private key or use them to create the information for the private key again to decrypt this information. So let's do this for the other 2 moduli as well. We could now use those values to calculate the remaining variables that we need, and then we could perform the decryption. But there's this cool script written by somebody where you can just give the script the PQ and moduli value, and it will generate a nice OpenSSL valid private key, which you then can use to let OpenSSL decrypt the data. Now let's save the script somewhere, and then let's see if we can execute that. Okay, so we are missing a Python module, so I create a virtual environment, and then I can enter this virtual environment and then install GMPY only for this particular session. So virtual environments are pretty cool for Python development, and if you do write scripts in Python, I highly recommend to you also use virtual environment. Okay, so there was another thing missing, but now it seems to work. Cool, so let's supply the arguments that we need, the PQ, the moduli, and the public exponent, and then we can execute it, and it will calculate the other values, especially this D value for us. -O, we can also specify a file we want to write the private key to. Cool, now we have a private key file. So let's do this for the other two public keys as well. Okay, now the second one and the third one. And if we print them, they look indeed like normal private keys. Now let's see if we can use the OpenSSL RSA utility to decrypt the file that was provided. But it doesn't look like so. We get an error. It's probably because all those 3 base 64 strings have to be first extracted and then decrypted with the specific private key on their own. Let's see if it just works with the base 64 string like that. So let's save this in a file and try RSA utility again. But nope, it still gives an error. So maybe we have to first base 64 decode it, and then we can maybe apply the private key to it. So let's save this output in a file and then try the RSA command again. And indeed, we get in weak. So that looks like part of the Internetwache CTF flag format. So cool. So let's do exactly the same thing with the other two base 64 strings. So let's do it with the second one. That seems to work. The second one with the third key, so the third one with the second key. And then we can combine those 3 strings properly together and we get the flag Internetwache Weak RSA keys are so bad. So let's move on to crypto70. Hash designer. There was the student hash design contest. All submissions were crap, but promised to use the winning algorithm. We hashed our password and got 0068 something. Brute force isn't effective anymore, and the key algorithm had to be collision resistant. So did that work or not? We will see. The service is running on a TCP port somewhere, so we can connect to it and see what we have to do. So you need to provide your proof of work, a SHA-1 hash with the last 2 bytes set to 0. And it has to have a certain specific prefix. And if we type in something else, it will just not let us pass and says it's wrong. So let's download also the zip file provided with the challenge and have a look at the files that we get. In this zip was a myhash Python script. Let's have a look at what it's doing. Looks complicated and seems to have nothing to do with this SHA-1 thing. I suggest we first look into passing the first barrier, which is brute forcing or finding a SHA-1 hash with a certain input which has a special prefix and produces a SHA-1 hash with 2 bytes set to 0. That's why I'm searching for the simple brute forcing algorithm for Python, so we can write a script to find such a SHA-1 hash. We also need some code to interact with the server, and I will just reuse code that I've written for the 32C3 CTF, which connects to the server and interacts with it and sends data and receives data. Okay, cool. Now we have some code to connect to a server, and specifically, more importantly, this receive all function, which pulls data until you receive a timeout. Let's start writing some code. First of all, we have to import a couple of things to use those code snippets here. We need import socket for the TCP connection to the server, and I use time because, sometimes you have to use a little sleep. We also have to define this variable server, which needs to have the IP address as well as the port we want to connect to. Stupid mistake here, the IP should be a string. I will realize and fix it in a second. But we can start to create now a connection to the server, and then we start to receive the first message when we connect to it. And obviously when I try to execute it now, I get the syntax error. So quickly fixing that, try it again. And we can read this message where it requires us to provide a proof of work. Now we just want to parse the string, so a very cheesy and very bad way, but it goes fast, is I just split the string from the spaces, and then at always the same position of this new list, we will find the prefix that we need for the SHA-1 hash. And yeah, at offset 21, that seems to work. So we get the prefix, and now we can start to brute force a SHA-1 hash with that. Next, let's import hashlib so we can write the SHA-1 code. So H will be a SHA-1 instance. I always have to Google. I always don't remember exactly how it works. So let me just copy it. Then I remember I need the brute force code in this script here. That's a pretty cool, neat little code, which I often copy actually. It just creates a generator which will constantly create and brute force passwords based on the char set and the length that you want this password to be. So we start defining if we found a valid hash, and if not, we will constantly loop and continue to look for it. Then we use update on the SHA-1 instance with the prefix, which was required by the proof of work, and the random string to brute force the SHA-1 hash. To brute force a random string, which I append to the prefix, I use random from Python. It's not the fastest or coolest way, but it's very easy and quickly written. So I define an alphabet I want to choose, and then I create a list out of random characters, which I then join together to a string. So that's a pretty easy way how to do it. And then we can give this string that we just generated to hashlib. Just quickly checking how to get the hash. And once we have the SHA-1 hash of this input, we want to check if the last 2 bytes are 0. Because it's in hex format, those are the last 4 characters that have to be 0. And then we send the input that found this hash. Getting rid of some syntax errors, and then we should be good to go. Ooh, that went quick. We found a valid input with the correct prefix that produced a hash which has 2 bytes 0 at the end. But the issue is that it has the wrong length. We need an input that has to pass this test here, so it has to be 15 characters long. So I fixed the generation of the random string, but we still get that it has a wrong length or wrong prefix. So maybe the 15 characters have to be included with the prefix, so I have to check the length of the prefix and then generate the missing amount of random characters afterwards. Looking for the hash, and we found one. And then it says, please continue with the login process, and asks us for a password. So that's pretty neat. That worked. We found a valid hash. We can also maybe print the hash output just to see that the last 2 bytes are in fact 0. So let's generate it again, super fast, and we found a valid hash with a certain prefix of the input that produces a hash with 2 0 bytes at the end. Okay, so let's continue with the next step of this challenge. We were provided another hash algorithm that we probably have to find a collision for because it's asking for a password. Now I'm poking just what it requires, and when I send the same password again, it says that the string has to be at least 18 characters long. The next part doesn't have to be interactive because the hash is fixed in the challenge description, so we just have to find one valid password that generates this hash that it's comparing to. And I also realized that I don't need the brute force code that I first got because my Python list joining is pretty effective, I guess. So now I'm just modifying the code that was already provided because it has the algorithm for the hash calculation inside. So let's create a random string that is 18 characters long, and then call the function to generate a hash. So my hash of the password that I've generated. So let's try it out, but alphabet is missing, so quickly fix that. We can check if the hash works, and yes, we generate a lot of different hashes. So now I just have to get the hash that is required and make a check for when we find this hash. And then we want to simply print the input that produced this special hash. So let's let it run. Let's see how fast we find the valid input. It takes a couple of more seconds than the SHA-1 brute force. More seconds than the SHA-1 brute force, but I'm sure eventually we will find one. Okay, after a minute or so, we found an input that produces the same hash. Now let's plug this into our original script that is interacting with the server and send the password, and then we should be done, I guess. So let's make this small modification of the code, sending this fixed password that we now know, and then let's run it. And indeed, we found the password. Fuck you, hash my ass. Let's head to the third crypto challenge that I'm showing off, which is crypto90. It's a bank. Everyone knows that banks are insecure. This one is super secure and only allows 20 transactions per session. But I always wanted to have $1 million, so let's see what we are dealing with. Again, we are given servers running on a TCP port 10061, and when we connect to it, we are presented with the bank backend, where we can create new transaction with a certain amount. So I just play around with it, get a feeling for this program. So we create one transaction, we create a transaction for $999. But if we try to create a transaction with too much money, it will not work. And with every transaction we initiate, we get a verification code, which we can use to complete a transaction using the ID of the transaction and this transaction code. Then this transaction will be executed and we get the money on our bank account. But the issue is we are only allowed 20 transactions. So how would we ever reach $1 million if we are not allowed to make transactions for those high numbers? So there must be a flaw in there somehow. So let's have a look at the code. We can see this is the main menu here, where it checks the command that we input. And if it starts with create, it will call eventually this create t function. As a parameter, it uses this a, which is an integer from the command that we supply. And create t seems to create a new transaction. And this transaction is then appended to the internal transaction underscore t list. And also the a, the number that we supply, is not allowed to be over a certain maximum, in this case over 5,000. So 5,000 works, but 5,001 will not work. But if we supply a lower value, then eventually we will create a new transaction and will get appended to this one list. So a new transaction gets created also with this parameter a, so that's the amount that we want to create a transaction with. And there's also the length check of the self underscore t list, that it will not be bigger than 20 transactions. So transaction will be initiated with the amount and this random value. This has probably something to do with the verification code. And then there's this also v variable, which is a boolean, which is default set on true. And when we complete a transaction and we try to complete it again, it says that we cannot complete the transaction twice. So there seems to be some protection, and that is what this v value is. If we already verified a transaction, this value will be set to false, and we are not allowed to validate another transaction. Anyway, once we created a valid transaction, the next step is that we call encrypt on this other class, and we encrypt this t variable, and t is the transaction that we created that was returned by create t. And the result here, this tc, will be printed as the verification code. So this encrypt creates this verification code that we need to verify a transaction. So we have the cipher class here, which defines a crypt, and it does some calculations. So it gets an x for it, and this x is complicated, calculated. And there also is this k value that was randomly generated before, and it's randomly with every transaction that we create. So let's debug this a little bit. Just use good old print debugging. Let's just put in a bunch of prints of important variables to see what is behind them and how this encryption actually works and what exactly is encrypted and how the output looks like. You also notice that this is a for loop over probably characters, and then the character gets XOR'd with this number that is generated somehow. So this is an XOR encryption. So what we will do is I will create a list where I append this XOR encryption key and have a look at it as well. How does it actually look like? And then we do the same for decrypt. Let's print there also some interesting values. But then I realized there's a problem with how I print the key that is used for the XOR, because generate next will then completely screw with the encryption. So we have to assign this encryption key to a variable k first so that we encrypt with the same one value that we also print. Cool, so let's try this and let's see what's behind those decryption and encryption functions. That doesn't work. We need to import the flag. Obviously the server has this flag then in a special file. So let's create this module so we can actually run this Python program locally. It's just an easy variable that is set in this file, and a Python module is also just a Python file, so that's easy. Anyway, so we started now, we can run it, and let's create a new transaction with 5,000. Okay, so it encrypts the string in capital letters transaction : space 5,000. And the list behind that, those are the XOR keys that are used for the XOR algorithm. And when we now complete this transaction, it will decrypt that string, and out of it comes the transaction 5,000 again. That's pretty cool. Now let's have a look at the complete function, what it does. So it reads the data from the command line, checks if this transaction ID is even valid, and checks if the verification has the correct length. And then it initiates the decryption. And it initializes this encryption with the transaction ID that was supplied. And out of this decrypt function comes a variable tn, and that tn is then added to A, and A is the account. So whatever decrypt does, the tn that comes out will be added to our account. So when we look at decrypt again, it takes two parameters, t and ct. And t is the transaction that we want to verify. And ct is the encrypted string, so this verification code, which is actually, an encrypted string. It's not a hash or something. So what it does then after the decryption, it replaces, or rather removes, the transaction string part of it. And so what is left over is only the number, the transaction amount that you want to have. And that is converted to an integer. And then the transaction amount is set to this number. This means that if we are able to modify the transaction amount in this encrypted verification code, we would be able to set a new different amount. And that is actually easier than it may seem on first sight. So let's create a new transaction. So we created a new transaction with 5,000. So how can we now modify this 5,000 with a higher number, maybe like 9,999? So now it changed, if you look closely, it changed a few bytes at the end, and the value changed. And if we look at our balance, we actually got those 7. So the idea we just had really works. If we are able to modify the amount that is inside of this transaction, we are able to get much higher numbers on much more money on our account. And of course, we want to get more than 1 million, because when we get more than 1 million on our account, the flag will be printed. So we have to do at least 20 transactions with 50,000 to actually reach this goal. But it seems like even if we could flip all the values in this encrypted string to 9999, it may not fit. Because remember, the verification code is only allowed up to a certain length, and obviously we cannot simply add stuff to it. But before I get to how we can exploit this, let's start writing the script that will talk with the server. So I create a new script, and I base it on the previous crypto level. So I just replace the part where we interact with it. So what we want is basically, we first want to create 20 transactions, and then we get the verification codes for it, and we remember the verification codes for now. And then we have to come up with an idea how we can turn those verification codes into something that will create much more money for us. And maybe you already had the idea when you saw that the encryption is XOR, because we know the plain text of those transactions. And when we know the plain text and we know how the encrypted transaction string looks like, then we can also get the keys by simply XORing the hash verification code with our transaction 500 string. And with those keys then, we can then create a new transaction which will have different values, or which will include whatever we want. So let's define a new function that we use to get the XOR key from a certain transaction given the verification code. So let's test this for now with only a true transaction we create, and then we have the codes in this list. We loop over this list and print the XOR keys. And yeah, looks pretty good. And with those keys now, we can obviously create a transaction that includes a different amount of money. So we have to define a new function, which will take the keys that we leaked and the string that we want to XOR, which will be the transaction amount, and then we return that, and then that should already work. So for each code that we get now the keys, and then we create the new verification code. So for each transaction code, we create now a new verification code with the string transaction 9999. That seems to work. And then we send this to the server with the confirm command, which is actually not confirm, I made a mistake, it's complete. So we have to provide the transaction ID and then the verification code. So now that works, and now we get our balance, and we see this indeed it works. Our balance is much higher than it used to be, and we got the $9,999 with each transaction. So the logical next step is to increase the amount we want to get. But the issue is now that it doesn't work, mainly because we don't have enough keys to encrypt the next character. But also I think the verification length would be too long with it. Not 100% sure right now. But there's another trick you can do to get the higher amount, and that is with this space. Because if you look at the replace method, it just replaces the colon, it doesn't care about the space, and the int function just strips away the space. But so we don't need the space, we can remove the space, we win one more character, which we can replace then with another 9. So now we should be able to get 99999. So let's run this, and indeed we got almost 200,000 amount money. So now we just have to increase the for loop to more transactions, and we should be able to get the 1 million money. So let this run, takes a couple of seconds. First we create all those transactions with 5,000. We have collected now all verification codes, and now we modify each verification code and step through it, and boom, we got the million. There's the flag. Shut up and take my money. So let's copy the flag and let's hand it in. Correct flag. Awesome, we solved crypto90.